Hello everyone. Today I'm glad to introduce the work QFactory, accelerating large language model serving with Qtile-graphs. This work is conducted by Qihao, Zhang, and other colleagues from Pac-Man Group in Tsinghua University. The first author could not be here today due to the visa issues. Okay, first, let me start with some background on serving quantized LLMs. With the even increased size of LLM, serving large language model has become more and more challenging. The increasing GPU memory capacity failed to catch up with this trend. Serving large language model like DeepSeek R1 requires substantial resource that many users cannot afford. Quantization has emerged as a possible solution for reducing the high deployment of LLMs. In quantized LLM, model rate is compressed and stored in low precision formats. For example, from half precision floating point to 4-bit integer. This reduced the memory requirement to about 1/4 of the original. The compression used a shared scaling factor to map the value from FP16 to the small integer 4 range. And during inference, the compression rate must be dequantized back to half precision before compute with activation, which is also in FP16. Now, let's take a closer look at how to run inference in quantized LLM. As inference evolved, two main operations, like element-wise multiplication and jam, a straightforward approach is to run them into two separate kernels. However, this will cause the intermediate result to be saved back to memory, and as a result, it increased the memory footprint and overload speedup, since it involved two additional memory access to the rate tensor. To enable efficient inference with quantized LLM, we need to fuse the quantization directly into jam operation. We refer such fused kernels as quantized operators. Here, we explain the motivation of this work. First, current quantization algorithm is moving to a fine-grained quantization to better preserve model accuracy. Besides scaling factor, an additional quantization parameter 0 point is introduced in symmetric quantization. In this way, we can make better use of the full range of info data type. However, symmetric quantization makes the quantization more complex and introduce extra memory overhead, which make implement quantized operators more challenging. On the other hand, quantization parameters are often shared in certain granularity. The scaling factor and 0 point is not shared per tensor, but per group. And the groups can have different layout. So in this percent example, the tensor is split into two 3x2 blocks, each process a scaling factor and a 0 point. Current solution for developing quantized operators can be divided into two categories. The first category is handcraft library like Merlin. This library typically achieves optimal performance and high hardware utilization, but they are often targeted to specific hardware and algorithm and require significant expertise and manual tuning. Consequently, an alternative approach is to enhance existing machine learning compilers to support low-precision computation. BitBars achieve this goal by expanding the data type to low precision in current LLM compilers. However, we found that it can only achieve suboptimal performance on generating fine-grained quantization operators. So here, the question is, can we achieve optimal performance with compilers? And our answer is yes. And to make this possible, we rely on two key insights. First, we discover current system process the extra dequantization in an eager execution paradigm. In other words, with eager execution, quantized tensor in the computation graph are immediately dequantized before execution. This rigid behavior limits the ability to explore different computation graph transformation. Instead, our insight is dequantization can be deferred. In the example, we first partial dequantize the quantized tensor with 0 point and scaling factor to quantized tensor with only 0 points. This allows to transform the graph in different but equivalent ways, generating multi-valid computational graph. This graph may have different computational overhead, which open up an opportunity for better performance. By deferred quantization operation, the searching space of computation graph is expanded. The second insight is that input in quantized operators may have different reuse frequency. Take the symmetrically quantized gem as example. To compute the metric multiplication, we typically assign different threads to different values in the result tensor. Let's take a look on the memory access pattern of the thread 2, 3, and 4. Each thread loads a row from activation and column from weight, perform a reduction, and multiply the result by the scaling factor. From this figure, we can see that different input tensors have different reuse patterns. The activation is shared across threads and gets reused, while the rate tensor is not reused between threads. The quantization parameters, the scaling factor, is reused based on the group pattern. For example, here, thread 2 and 3 share the same scaling factor, while thread 4 use different scaling factor. In this way, it requires reuse pattern-aware memory scheduling. Based on the above insight, we propose QFactory, an efficient compilation framework for generating quantized kernels. QFactory introduced a novel abstraction for quantized tensor called Qtile, which serves as critical bridge between quantization algorithm and efficient kernel implementation. At the entry point, QFactory accepts the quantized program and transform it into Qtile-graph. After that, QFactory applies Qtile computational transformation to explore different equivalent Qgraph candidates. To optimize overall performance bandwidth utilization, QFactory further employs differentiate Qtile scheduling to maximum data reuse. And finally, QFactory generates the kernel with templates. Essentially, Qtile is a tensor extent with annotation of quantization attribute. We conclude two key configs in quantization algorithm. The first is mapping function with quantization parameters, and second is quantization group pattern. The mapping function encodes all detailed information required for performing dequantization, including quantization algorithm and auxiliary parameters. Group pattern describes the granularity of quantization, and it can be used to guide the memory scheduling processing. With such Qtile abstraction, QFactor first replaces certain tensor in the computation graph with quantized tensor, thereby form a Qtile graph. Next, Qtile performs a BFS-like Qtile propagation on the graph and generating candidate Qgraph by applying transformation rule to matching the subgraph. To determine whether a transformation can be made, we deduce the result of Qtile computation based on the mathematical equivalent. By performing equivalent transformation, the quantization method can be shifted and more equivalent computation graph can be explored, and therefore resulting in potential performance benefits. For more detail, please refer to the paper. After the graphic level transformation, QFactory conducts differentiate Qtile scheduling to make use of GPU memory bandwidth. As we know, modern GPU are equipped with hierarchical memory system, including 4 layers of registers, L1 and L2 cache, and memory. To perform computation on GPU, data must be transferred from memory to register. Encoder expose user configurable shared memory for mapping L1 layer memory, but L1 and L2 cache are still transparent to the programmers. However, the cache operator in PTX instruction allow us to set the eviction policy. When we setting cache policy to evict first, the memory pollution in cache is minimized, and which create a loading path that bypass intermediate cache layer. To summarize, we now have multi-load paths in GPU memory system. With the differentiate data loading path, QFactory schedule different input tensor tied to different layer and loading paths. For example, here, QFactory maps weight tensor tied directly from memory to register, while caching activation and quantization parameters in the intermediate cache layer. With this different schedule policy, we can maximum the overall memory bandwidth and therefore improve the performance. Now, I'm going to present the evaluation part of QFactory. We conduct our evaluation on 3 different GPU platforms, including V100, 800, and H100. We also conduct kernel-level evaluation on various matrix shapes. To test end-to-end performance, we integrate QFactory into VLLM, a widely used LLM serving framework. For kernel-level performance, QFactory consistently outperforms baseline across different GPU platforms and bandwidth. It achieves a comparable performance with the handcraft library Merlin on 800 and surpass it on H100 by 1.3 times. For end-to-end performance, QFactory achieves up to 1.5h speedup in quantized LLM decoding. To conduct ablation study, we progressively apply our optimization techniques and the performance gradually advance. For more evaluation results, please refer to the paper. In conclusion, QFactory is a compilation framework based on the novel Qtile abstraction. We apply Qtile computation transformation at the graph level and introduce differentiate Qtile schedule at the operator level. This helps us to explore a large search space and improve memory bandwidth utilization, and also improve the performance. As a result, QFactory achieved an average speedup of 1.66 times compared to existing system. If you have any question, feel free to reach out to us through the email shown on the slide. Thank you for your attention.